Right now, as you're listening to this, something impossible is happening. You're living inside a contradiction that most people never realize. We call our planet warm, we see green forests and flowing oceans, we watch summer arrive every year like clockwork. But here's the truth that's going to shift your perspective on everything. You are living in an ice age, not approaching one, not recovering from one, living in one right now. This very moment, the ice age that began 2,600,000 years ago never actually ended. It's still here. We're just experiencing a warm pause, a temporary break in a pattern that's been repeating for longer than our species has existed. And the wildest part, the part that's going to keep you thinking long after this video ends, is that this pattern operates on a rhythm so precise, so mathematically perfect, that it almost seems planned. Every 100,000 years, give or take a few millennia, our planet transforms. Massive ice sheets grow and cover entire continents. Then they retreat. Then they grow again. Over and over and over, like a cosmic metronome beating out the rhythm of geological time. So why does this happen? What force is powerful enough to freeze and thaw an entire planet on such a precise schedule? The answer is going to take us on a journey through orbital mechanics, extinct giants, and human survival against impossible odds. Before we dive deep, do me a favour. If you're enjoying this kind of content, hit that like button. It genuinely helps these videos reach more people. And drop a comment telling me where you're listening from and what time it is. I love seeing the global reach of these stories. Someone in Tokyo at 3 in the morning, someone in Berlin during their morning coffee, someone in California winding down for sleep. The internet makes these connections possible in ways that would seem like magic to our Ice Age ancestors. But speaking of our ancestors, let's talk about what they faced. Because understanding the 100,000-year cycle isn't just about abstract science. It's about understanding the world that shaped us. The creatures that lived during the cold phases of this cycle were unlike anything alive today. We're talking about animals so massive, so perfectly adapted to frozen conditions that they seem almost mythological. Woolly mammoths with fur a metre long trudging across endless grasslands. Giant ground sloths, the size of elephants digging tunnel systems underground. Saber-toothed cats with fangs like curved daggers hunting prey that weighed tons. These weren't fantasy creatures from movies or books. They were real animals that dominated Earth for hundreds of thousands of years. And here's what's haunting about their story. About 10,000 years ago, as the cycle shifted from cold to warm, most of these magnificent creatures vanished. Gone. The megafauna that had thrived through countless cycles before suddenly couldn't survive this one. We're still debating exactly why. Was it the speed of climate change? Was it human hunting? Was it both working together in a perfect storm of extinction? The answer matters because we're facing our own moment of rapid climate change right now, and understanding what happened to the Ice Age giants might tell us something crucial about our own future. So in this video, we're going to unpack the entire mystery. We'll explore the orbital mechanics that drive the 100,000-year pattern. We'll meet the scientists who figured it out. We'll walk among the megafauna and understand how they survived in a frozen world. We'll follow early humans as they adapted and innovated. And we'll trace the dramatic transition that ended the last ice age and brought us into the world we know today. Then we'll connect it all to our current moment, because this ancient pattern has urgent implications for our future. By the end, you're going to understand Earth's climate in a completely new way. You'll see how small changes in our planet's position relative to the Sun can trigger massive transformations. You'll understand why the number 100,000 keeps appearing in climate records, and you'll grasp why this matters profoundly for the decisions we make today. Let's start with a simple question that opens up an entire universe of complexity. What actually is an ice age? The term ice age gets thrown around casually, but most people don't actually know what it means. So let's get precise. An ice age isn't just a cold winter or even a cold century. It's an extended period of time, we're talking millions of years here, when Earth's temperature drops enough that permanent ice sheets and glaciers cover significant portions of the planet's surface. The key word there is permanent. These aren't seasonal snowfalls that melt in spring. These are ice masses that persist year after year, century after century, millennium after millennium, growing slowly, pressing down on the continents beneath them with unimaginable weight. We're currently living in what scientists call the Pleistocene Ice Age. This particular ice age started approximately 2,600,000 years ago. Think about that time frame for a moment. 2.6 million years. Modern humans, Homo sapiens, have only existed for about 300,000 years. Our species emerged well after this ice age had already been running for over 2 million years. The Pleistocene ice age is still technically ongoing. We haven't left it. We've just entered a warmer phase within it. And this is where the terminology gets important because it confuses a lot of people. Within any ice age you get fluctuations. These fluctuations divide into two types of periods. Glacial periods, when it's really frozen, when ice sheets expand to their maximum extent. And interglacial periods, when it warms up and ice sheets retreat to smaller areas. We are currently in an interglacial period. It's called the Holocene, and it began 11,700 years ago. So when most people say the Ice Age, what they actually mean is the last glacial period. That's the cold phase that lasted from roughly 115,000 years ago until 11,700 years ago. During that glacial period, ice sheets were at their biggest extent, and the megafauna we mentioned earlier were running the show across vast stretches of the planet. Now here's something that surprises people. The temperature difference between a glacial period and our current interglacial isn't actually that dramatic in terms of raw numbers. We're talking about 6 degrees Celsius colder on average. 6 degrees? That doesn't sound like much, right? Your thermostat at home varies more than that between day and night. But here's the crucial thing to understand. We're not talking about 6 degrees in one location or even one region. We're talking about 6 degrees Celsius worth of thermal energy being sucked out of the entire planet. All the oceans, all the land masses, the whole atmosphere. When you remove that much heat from a global system, the results are absolutely transformative. Those 6 degrees were enough to completely reshape Earth's surface. Huge ice sheets, some more than 3 kilometers thick, covered most of Canada and extended down into what's now the northern United States. Europe had its own massive ice sheet blanketing Scandinavia, the Baltic region, parts of Britain, and northern Russia. These weren't just big glaciers. These were continental ice sheets containing millions of cubic kilometers of frozen water. The weight was so enormous that it actually deformed the Earth's crust beneath, pressing the solid rock downward. And here's where it gets really dramatic. All that ice had to come from somewhere. It came from the oceans. As water evaporated from the oceans and fell as snow on the growing ice sheets, it got locked up on land instead of returning to the sea. The result was that sea levels dropped, not by a few meters, by over 120 meters. That's as tall as a 40-story building. Imagine standing at the current shoreline and looking out 120 meters above the ocean surface. That's where the beach used to be during the last glacial maximum. Coastlines extended way beyond where they are today. The English Channel didn't exist as a body of water. You could walk from England to mainland Europe on dry ground. The Persian Gulf was a river valley, not a gulf. Indonesia, which today consists of thousands of separate islands, was mostly a single connected landmass joined to mainland Asia. Australia, New Guinea, and Tasmania formed one giant continent. And between Alaska and Siberia, where the Bering Strait exists today, there stretched a massive grassy plain called Beringia. The world map looked completely different. Continents had different shapes. Islands were connected. Oceans were smaller. It was a genuinely alien planet compared to what we know today. But it wasn't just the geography that changed. The climate itself was radically different in ways that go beyond simple temperature. For most of human history, people had no idea why ice ages happened. They knew the world had once been colder because they found strange things buried in the ground. Enormous bones belonging to creatures that no longer existed. Boulders sitting in places where no boulders should be, clearly carried there by some immense force. Scratches carved into bedrock suggesting that something massive had scraped across the landscape. But the cause remained a complete mystery. Religious explanations dominated for centuries. Then early scientists started proposing theories. Maybe volcanic eruptions blocked out the sun. Maybe the Earth passed through cold regions of space. Maybe ocean currents shifted dramatically. All interesting ideas, but none of them could explain the pattern. Because by the late 1800s, geologists had figured out something remarkable. Ice ages weren't random one-time events. They happened repeatedly. There was a pattern, a rhythm, though nobody could explain what was driving it. Then in the early 1900s, a Serbian mathematician named Milankovitch had an idea that would change everything. Milankovitch wasn't a geologist or a climatologist. He was trained in mathematics and astronomy. And he approached the Ice Age problem from a completely different angle than anyone before him. What if, he wondered, Ice Ages weren't caused by anything happening on Earth at all? What if the cause was astronomical? What if Ice Ages were driven by subtle changes in Earth's position and orientation relative to the Sun? At first this seems absurd. Earth orbits the Sun, sure, but that orbit is stable, right? We're the same distance away, year after year, century after century. Except that's not actually true. And this is where Milankovich's genius came in. He understood that Earth's orbit isn't perfectly stable over long time periods. It changes. Slowly, gradually, but measurably. And those changes affect how much sunlight hits different parts of Earth at different times of the year. Milankovitch identified three main cycles, three different ways that Earth's orbital relationship with the Sun changes over time. Let's start with the first one, the one that gives us our 100,000-year pattern. It's called eccentricity. Earth's orbit around the Sun isn't a perfect circle, it's an ellipse, slightly stretched out. But the amount of stretching varies over time. Sometimes the orbit is more circular, sometimes it's more elliptical, more elongated. This variation happens because of gravitational pulls from other planets in our solar system, mainly Jupiter and Saturn. These giant planets tug on Earth as we all orbit the Sun, and over long time scales those tugs change the shape of Earth's orbit. The orbit cycles from more circular to more elliptical, and back to more circular again. And this complete cycle takes approximately 100,000 years. 100,000 years. There's our number. When Earth's orbit is highly elliptical, the distance between Earth and the Sun varies more dramatically throughout the year. During part of the orbit we're closer to the Sun, during another part we're farther away. This affects how much solar radiation hits the planet at different times. But here's the thing that Milankovitch understood, and this is crucial. It's not about the total amount of sunlight Earth receives over a year. That stays roughly the same regardless of orbital shape. What matters is the distribution of that sunlight. Where does the sunlight hit? When does it hit? And this is where the second cycle comes in. It's called obliquity, which is just a fancy word for axial tilt. You know how Earth spins on an axis, and that axis is tilted relative to our orbital plane? That's why we have seasons. When the northern hemisphere tilts toward the Sun, we get northern summer. When it tilts away, northern winter. But the amount of tilt itself isn't constant. The angle varies between about 22.1 degrees and 24.5 degrees. Right now, we're at about 23.5 degrees and slowly decreasing. This tilt variation happens on a cycle of approximately 41,000 years. When Earth has more tilt, the seasons are more extreme. Summer is hotter, winter is colder. When Earth has less tilt, the seasons are milder. Summer isn't as hot, winter isn't as cold. And here's why this matters for ice ages. If summer isn't warm enough to melt all the snow that fell during winter, that snow sticks around. Year after year it piles up. Eventually you've got ice sheets forming. The third cycle is called precession. Imagine Earth as a spinning top. If you've ever watched a top spin, you know that as it slows down, it starts to wobble. Earth does the same thing. Our rotational axis wobbles like a slowly spinning top. This wobble is called precession, and it happens on a cycle of approximately 26,000 years. Precession changes which hemisphere points toward the Sun during different parts of Earth's orbit. Right now, the Northern Hemisphere experiences winter when Earth is closest to the Sun in its elliptical orbit. That makes northern winters milder than they would otherwise be, but during other parts of the precession cycle, that relationship flips. Northern Hemisphere winter occurs when Earth is farthest from the Sun, making those winters much colder. When you combine all three of these cycles together, eccentricity, obliquity and precession, they create complex patterns of solar radiation hitting different parts of Earth at different times of year. And Milankovitch worked out the mathematics. He calculated exactly how much solar radiation reached various latitudes during different seasons over the past 600,000 years. His calculations predicted that there should be periods when Northern Hemisphere summers are cool enough that winter snow doesn't fully melt, and during those periods ice sheets should grow. The predictions matched the geological evidence beautifully. Milankovitch had figured it out. Ice ages are driven by astronomical cycles, not by anything happening on Earth, but by the slow, predictable dance of orbital mechanics. Now here's where things get genuinely weird, and this is the part that kept scientists puzzled for decades after Milankovitch published his work. When you look at the three orbital cycles, eccentricity at 100,000 years, obliquity at 41,000 years, and precession at 26,000 years, you'd expect the stronger cycles to dominate the climate pattern. And by stronger, I mean the cycles that cause bigger changes in solar radiation. Turns out, eccentricity is actually the weakest of the three in terms of how much it changes the amount of sunlight hitting Earth. The variations in axial tilt and the wobble of precession both cause much larger swings in seasonal sunlight than eccentricity does. So logically, you'd expect the 41,000-year cycle or the 26,000-year cycle to show up most prominently in climate records, but that's not what happened. Starting in the 1960s and 70s, scientists developed new techniques for reconstructing past climate. They drilled cores out of ocean sediments and ice sheets, extracting long cylinders of material that had been laid down layer by layer over hundreds of thousands of years. These cores are like history books written in ice and mud. Each layer contains information about the climate when it formed. Tiny shells of marine organisms preserve the chemical signature of ocean temperature. Bubbles trapped in ancient ice contain samples of the atmosphere from millennia ago. Pollen grains show what plants were growing. Dust levels indicate how dry and windy conditions were. When scientists analysed these climate records, looking for patterns and rhythms, they found something unexpected. The dominant pattern wasn't 41,000 years or 26,000 years. It was 100,000 years. The weakest orbital cycle was somehow controlling the show. This became known as the 100,000-year problem, and it puzzled scientists for years. How could the weakest forcing create the strongest response? It seemed to violate basic physics. If you push something gently, you expect a gentle response. If you push something hard, you expect a strong response. But climate was showing the opposite pattern. A gentle push from eccentricity was producing massive ice age cycles, while stronger pushes from obliquity and precession seemed to take a back seat. The solution to this puzzle involves something called feedback mechanisms. Climate doesn't just respond passively to external forcing. It has internal amplifiers that can take a small initial change and magnify it into something much larger. Think of it like a sound system. The signal coming from your phone is tiny, just a few milliwatts of power, but the amplifier takes that weak signal and turns it into sound loud enough to fill a room. Climate has similar amplifiers built into it. Here's how it works with ice sheets. When orbital cycles create conditions favourable for ice sheet growth, snow starts accumulating in northern regions. That snow is white, and white surfaces reflect sunlight back into space instead of absorbing it. This is called the albedo effect. As more snow accumulates, more sunlight gets reflected, which cools things down further, which allows even more snow to accumulate. It's a self-reinforcing loop. Once it starts, it amplifies itself. The same thing happens in reverse. When conditions shift toward warming and ice starts melting, you expose darker rock and soil underneath. Darker surfaces absorb more sunlight, which warms things up more, which melts more ice. Another runaway process, but in the opposite direction. These feedback loops can amplify weak initial forcing into powerful climate changes. But that still doesn't fully explain why the 100,000-year cycle dominates. The current best explanation involves asymmetry in how ice sheets grow versus how they collapse. Ice sheets take a long time to build up. Snow falls year after year, gradually accumulating. The ice gets thicker and spreads outward slowly. This process can take tens of thousands of years, but ice sheets can collapse much more quickly. Once they reach a certain size, they become unstable. Warm ocean water can get underneath them. Meltwater can lubricate their base, causing them to slide faster. Sections can break off and float away as icebergs. What took 50,000 years to build might disappear in 5,000 years. This asymmetry means the climate system spends most of its time slowly building ice, then rapidly melts it away, then starts building again. The long build-up phase tends to last about 80 to 90,000 years. The warm interglacial phase lasts about 10 to 20,000 years. Add them together and you get cycles averaging around 100,000 years. The weak eccentricity forcing might be just enough to trigger the transitions between these states, even though it's not the strongest cycle. It's like a light switch. You only need a tiny amount of force to flip a switch, but flipping that switch can turn on powerful lights. Eccentricity acts as the switch that triggers much larger changes amplified by feedbacks. This is still an active area of research. Scientists continue refining their understanding of exactly how these cycles interact with feedback mechanisms to create the patterns we see in climate records. But the basic picture is clear. Earth's climate responds to astronomical forcing in complex, non-linear ways. Small changes in orbital parameters can trigger massive planetary transformations when those changes interact with internal feedback loops. And for the past million years or so, the result has been a remarkably regular rhythm. Ice sheets grow slowly over tens of thousands of years. Then they collapse relatively rapidly. Then they grow again. 100,000-year cycles of freeze and thaw, creating wildly different worlds during the cold phases versus the warm phases, and during the cold phases, life on Earth adapted to create some of the most extraordinary creatures ever to walk the planet. Let's dig deeper into this asymmetry because it's crucial for understanding why ice ages behave the way they do. Imagine you're building a sandcastle on a beach. Building it takes time and effort. You carefully pile sand, pack it down, shape the towers, dig the moat. Maybe it takes you an hour to construct something impressive, but destroying it? A single wave can wipe it out in seconds. Ice sheets follow a similar pattern, except the timescales are thousands of years instead of minutes. During the growth phase, everything happens gradually. Snow falls each winter in high northern latitudes. Some of it melts during summer, but if summers are cool enough, not all of it melts. The leftover snow gets buried by next winter's snowfall. Year after year, layer upon layer. As the snow pile gets thicker, the weight compresses the bottom layers into solid ice. Over centuries and millennia, this ice mass grows larger and spreads outward under its own weight. The edges of the ice sheet slowly advance across the landscape, covering more territory. But ice sheet growth isn't just about snow accumulation. Remember those feedback loops we mentioned? They kick in powerfully during the growth phase. Fresh snow is incredibly reflective. It bounces about 80 to 90% of incoming sunlight back into space. As the white area expands, the planet's overall albedo increases. More reflected sunlight means less absorbed heat. Less absorbed heat means cooler temperatures. Cooler temperatures mean more snow survives summer. More surviving snow means larger white areas. The loop feeds itself. There's another feedback involving carbon dioxide. As temperatures drop and ice sheets grow, the oceans absorb more carbon dioxide from the atmosphere. Cold water holds dissolved gases better than warm water. Same reason your soda goes flat faster when it's warm. With less carbon dioxide in the atmosphere, the greenhouse effect weakens. Less greenhouse warming means cooler temperatures, which allows more ice sheet growth. Again, self-reinforcing. These positive feedbacks don't make ice sheets grow quickly. They just ensure that once growth starts, it continues. It's like rolling a snowball downhill. Gravity pulls it down, and as it rolls, it picks up more snow, getting bigger and heavier, which makes it roll faster and pick up even more snow. Ice sheets are the climate equivalent of that snowball rolling very, very slowly downhill over tens of thousands of years. But here's where the asymmetry becomes dramatic. Ice sheets don't shrink in a nice, orderly, gradual way. They collapse. Think about the structure of an ice sheet. It's not just sitting on land like a giant ice cube on a table. Parts of it extend out over the ocean, forming ice shelves. The ice is so thick and heavy that it flows like an extremely slow liquid, spreading outward under its own weight. The edges reach the coast and keep going, floating on seawater. These ice shelves are important because they act like buttresses, supporting the ice on land behind them and slowing its flow toward the ocean. When warming begins, several things happen quickly. Warmer air melts the surface during summer. That meltwater trickles down through cracks in the ice until it reaches the bedrock below. Now you've got water lubricating the base of the ice sheet. Suddenly the ice can slide much faster across the underlying rock. It's like going from dragging a heavy box across rough concrete to sliding it across an ice rink. Meanwhile, ocean temperatures are rising too. Warmer seawater eats away at the floating ice shelves from below. As ice shelves thin and weaken, they eventually break apart. Without those buttresses holding it back, the land ice behind them accelerates its flow toward the ocean. Large sections can break off and float away as armadas of icebergs. What took 50 or 60,000 years to accumulate can disappear in just a few thousand years. The collapse phase has its own feedbacks, all working in the direction of amplification. As ice area shrinks, darker land and ocean surfaces get exposed. These darker surfaces absorb more sunlight instead of reflecting it. More absorbed sunlight means more warming. More warming means faster melting. Faster melting exposes more dark surface. Another self-reinforcing loop, but this time driving the system toward an ice-free state. Carbon dioxide returns to the atmosphere as oceans warm and release dissolved gases. More atmospheric carbon dioxide strengthens the greenhouse effect. Stronger greenhouse effect means more warming. More warming releases more carbon dioxide from the oceans. Yet another positive feedback driving rapid change. The transitions between glacial and interglacial states aren't gentle. They're relatively abrupt switches from one stable state to another. Climate scientists sometimes call these tipping points. You can push on the system for a while without seeing huge changes, but once you cross a threshold, the feedbacks take over and drive rapid transformation. This is why the 100,000-year pattern shows up so strongly despite eccentricity being the weakest orbital forcing. The climate system isn't responding linearly to the forcing. It's using weak periodic nudges from eccentricity as triggers to flip between stable states, with the transitions amplified by powerful internal feedbacks. Understanding this asymmetry and these feedback mechanisms isn't just academic. It has profound implications for our current situation. Because right now we're pushing on these same feedback systems, except we're pushing much harder and much faster than orbital cycles ever did. But we'll get to that later. First, we need to meet the creatures that thrived during the cold phases of these cycles. The megafauna that dominated Earth for hundreds of thousands of years. Animals so magnificently adapted to Ice Age conditions that they seemed perfectly engineered for a frozen world. The word megafauna literally means giant animals. And when we talk about Ice Age megafauna, we're talking about creatures that would dominate any room they walked into. Many of them weighed over 1,000 kilograms. Some exceeded 4,000 kilograms. For comparison, that's heavier than most modern elephants. Why did Ice Age animals get so huge? There's a biological principle called Bergmann's rule that offers part of the answer. It states that within a species, individuals living in colder climates tend to be larger than those in warmer climates. The physics behind this makes sense. Large bodies have a lower surface area to volume ratio. Imagine two cubes, one with sides of 1 centimetre, another with sides of 10 centimetres. The small cube has 6 square centimetres of surface area and 1 cubic centimetre of volume. That's a ratio of 6 to 1. The large cube has 600 square centimetres of surface area and 1,000 cubic centimetres of volume. That's a ratio of less than 1 to 1. Heat escapes through surface area, but the body generates heat based on its volume, so a larger animal loses proportionally less heat relative to its size. In freezing conditions, being big is a survival advantage. You stay warm more efficiently. That's why modern polar bears are bigger than other bear species. It's why Arctic foxes are larger than kit foxes from warm deserts. And it's why Ice Age mammals tended toward gigantic sizes. But size alone doesn't tell the whole story. These animals had incredible specialised adaptations for surviving in a world that would kill most modern creatures within hours. Let's start with the most iconic Ice Age animal, the creature that has become the symbol of the Pleistocene epoch, the woolly mammoth. When most people picture mammoths, they imagine creatures much larger than modern elephants. But actually, woolly mammoths were roughly the same size as today's elephants, maybe slightly shorter at the shoulder. An adult male stood about 3 to 3.5 metres tall. Females were smaller. So why do they loom so large in our imagination? Probably because of their spectacular adaptations. Mammoths were covered in thick, shaggy fur that could reach lengths of nearly 1 metre in places. This wasn't a single layer. They had dense underwool providing insulation close to the skin, and longer outer guard hairs that shed water and snow. This 2-layer system worked like the best modern winter clothing, trapping warm air close to the body while keeping moisture out. Underneath that magnificent coat, mammoths had a layer of fat up to 9 centimetres thick. This fat served dual purposes. It provided additional insulation against the cold, and it acted as an energy reserve during harsh winters when food was scarce. Compare that to African elephants, which have virtually no fur and very little subcutaneous fat because they need to release heat rather than conserve it. Their ears tell another story. Mammoth ears were small and rounded, nothing like the huge flapping ears of African elephants. Large ears are great for cooling off because they have lots of surface area filled with blood vessels. But in the Arctic, large ears would be a liability. They'd lose too much heat and would be vulnerable to frostbite. So mammoths evolved small ears tucked close to their heads. Even their skulls were specially adapted. Mammoths had large sinus cavities inside their skulls. These air-filled spaces served as natural heat exchangers. When a mammoth breathed in frigid air, it passed through these sinuses, where it was warmed and humidified before reaching the lungs. Breathing extremely cold, dry air repeatedly can damage lung tissue. These sinus cavities were crucial protection against that damage. We see the same adaptation in other Ice Age mammals, and even in modern cold-adapted species like reindeer. Their teeth deserve attention too. Mammoths had specialised molars perfect for grinding the tough grasses and sedges that grew on the mammoth steppe. Those teeth wore down over time from all that grinding, but mammoths had a solution. They went through 6 sets of teeth during their lifetime. As one set wore down, new teeth would move forward from the back of the jaw to replace them. Only when the final set wore out would a mammoth face serious problems feeding. We know an extraordinary amount about mammoths, because some have been found frozen in permafrost, preserved almost perfectly for tens of thousands of years. These aren't just skeletons. These are complete animals with fur still attached, skin intact, and even stomach contents preserved. Scientists have examined what they ate, finding remains of grasses, herbs, and flowers. They've extracted DNA and sequenced entire mammoth genomes. These genetic studies revealed something fascinating. Mammoths had special variants of hemoglobin, the protein that carries oxygen in blood. Normal hemoglobin doesn't work as efficiently in extreme cold. The chemical reactions that release oxygen to tissue slow down at low temperatures. But mammoth hemoglobin had mutations that compensated for this. Even when tissue temperatures dropped, mammoth blood could still deliver oxygen effectively. That's molecular level adaptation to Ice Age conditions. We've also found genes related to fat storage, sparse sweat glands, small ears, and insulating fur, all coded right into their DNA. Evolution didn't just change how mammoths looked on the outside, it rewired their biology at the deepest level. But as impressive as mammoths were, they weren't alone. The Ice Age world was populated with an incredible diversity of giant mammals, each with their own spectacular adaptations, and some of them were even stranger than mammoths. Woolly rhinoceros roamed the same frozen grasslands as mammoths, and they were just as impressively adapted. Similar in size to modern rhinos, they stood about 2 meters tall at the shoulder and weighed up to 2,000 kilograms. Like mammoths, they were covered in thick woolly fur. But their most distinctive feature was their horns. Woolly rhinos had 2 horns, and the front one could exceed 1 meter in length. Unlike the horns of modern African rhinos, which are relatively straight, woolly rhino horns were flattened from side to side and swept backward. We know what these horns were used for because we've found preserved specimens and studied wear patterns. Woolly rhinos used their massive front horns as snowplows. During winter, when snow covered the vegetation, they would sweep their horns back and forth, clearing away the snow to reach the grasses and herbs underneath. Imagine a 2-ton animal with a built-in shovel attached to its face, methodically clearing feeding areas across the frozen steppe. That's exactly what they were. Like mammoths, some woolly rhinos have been found frozen in Siberian permafrost, with their soft tissues intact. These specimens show the same kind of adaptations we see in mammoths. Small ears to reduce heat loss, thick layers of fat for insulation and energy storage, specialised nasal passages to warm, cold air. These animals weren't just surviving in Ice Age conditions, they were thriving. Now let's travel to the Americas, where a completely different group of giants lived. Giant ground sloths. If you've seen modern sloths, those adorable, slow-moving animals that hang in rainforest trees, you need to completely reset your mental image. Ice Age ground sloths were nothing like that. The largest species, called Megatherium, reached estimated body masses of 4,000 kilograms. That's heavier than most elephants. They could stand on their hind legs and reach heights of 4 meters or more. Picture an elephant-sized sloth standing upright. These weren't cute and cuddly. These were massive, powerful animals. Ground sloths were too large to climb trees, so they lived entirely on the ground, feeding on vegetation. They had long arms with enormous curved claws, perfect for pulling down branches or digging. And here's where ground sloths get really interesting. They dug burrows, actual underground tunnel systems. When scientists first discovered these burrows in South America, particularly in Argentina and Brazil, they didn't know what could have created them. The tunnels were enormous, some reaching 40 meters in length and nearly 2 meters in width and height. That's big enough for a person to walk through comfortably, though you probably wouldn't want to if you knew what made them. The walls and ceilings of these burrows have distinctive claw marks scratched into the hardened sediment. Researchers matched these marks to ground sloth hand skeletons, and they fit perfectly. The spacing, the angles, the depth, all consistent with ground sloth claws. Why were these massive animals digging subway system-sized burrows? Probably for the same reasons many modern animals dig. Protection from temperature extremes, shelter from predators, safe places to rest. Underground, temperatures stay relatively stable year-round. In summer it's cooler than the surface. In winter it's warmer. For an animal living in a region with significant temperature swings, a burrow provides climate control. The effort required to dig these tunnels must have been enormous, but ground sloths were built for it. Analysis of their skeleton shows incredibly powerful forelimbs with massive muscle attachment points. Their bones were dense and strong, capable of withstanding the stresses of digging through hard earth. And their centre of gravity was positioned over their hind legs, allowing them to rear up into a bipedal stance, freeing their front limbs for digging. They were nature's excavators. Crossing the size spectrum, we encounter another bizarre group of South American megafauna. Glyptodonts. Imagine an armadillo. Now scale it up to the size of a small car. That's basically what a glyptodont was. These creatures were distant relatives of modern armadillos, but they'd taken the armoured body plan to an extreme. Glyptodonts had shells made of hundreds of bony plates fused together into a single rigid dome. Unlike modern armadillos, which have flexible bands in their armour and can roll into balls, glyptodonts had completely rigid shells. They couldn't roll up, but they didn't need to. Their armour was thick enough and strong enough to stop almost any predator. The shell alone could weigh hundreds of kilograms. Walking around with that kind of protection required massive, elephantine legs. But the shell wasn't their only defensive adaptation. Some glyptodont species had tails covered in bony rings with large spikes at the end. These tail clubs looked like medieval weapons, and recent biomechanical studies suggest they were used the same way. Researchers analysed the muscle attachment points and joint structure of glyptodont tails and found they were built for powerful swinging motions. Combined with evidence that some glyptodonts could rear up on their hind legs, we get an amazing picture. These armoured tanks could stand upright and swing spiked clubs attached to their bodies. Any predator foolish enough to attack would face serious consequences. The diversity of defensive strategies among Ice Age herbivores is remarkable. Mammoths used size and tusks. Woolly rhinos had horns and aggression. Ground sloths had massive claws and possibly their burrows for retreat. Glyptodonts had armour and weaponized tails. Each species found its own solution to the challenge of surviving in a world filled with formidable predators. And those predators deserve their own introduction, because the Ice Age produced some of the most impressive carnivores ever to walk the earth. Where there are massive herbivores, there must be predators capable of taking them down. The Ice Age delivered on that requirement with a spectacular array of carnivores. Let's start with the most famous, saber-toothed cats. When people say saber-toothed tiger, they're usually thinking of Smilodon, which lived in the Americas. These weren't actually tigers, they were a completely different lineage of cats that evolved enormous canine teeth independently. And when we say enormous, we mean it. Those upper canines could reach 18 centimetres in length, curved backward like daggers, and flattened from side to side to create sharp cutting edges. But here's what's fascinating about saber-toothed cats. Despite those impressive fangs, their bite force was actually weaker than modern big cats. A lion can crush bone with its jaws. Smilodon couldn't. So how did they use those weapons? The answer comes from biomechanical analysis of their skulls and neck vertebrae. Saber-tooths had incredibly powerful neck muscles, far stronger than modern cats. The vertebrae in their necks have massive attachment points for muscles. Their hunting strategy wasn't about biting down hard, it was about precision stabbing. Here's how it probably worked. A Smilodon would use its powerful forelimbs to wrestle prey to the ground. Their front legs were heavily muscled, built for grappling. Once the prey was down and couldn't escape, this saber-tooth would position itself carefully and use its strong neck muscles to drive those long canines deep into the prey's throat or belly, severing major blood vessels. One precise strike causing rapid death from blood loss. It wasn't about crushing power, it was about surgical precision. We have incredible evidence for how common these predators were from a site in California called the La Brea tar pits. Thousands of years ago, natural asphalt would seep to the surface and form sticky pools. Animals would get trapped in these pools, and their distress would attract predators and scavengers, who would then also get trapped. Over tens of thousands of years, the bones of these trapped animals accumulated. Paleontologists have excavated La Brea extensively, and they found thousands of saber-toothed cat fossils, more than from any other location on Earth. This tells us several things. First, saber-tooths were common, not rare. Second, they were probably social animals living in groups, because the pattern of fossils suggests multiple individuals coming to investigate trapped prey. Third, They were successful hunters taking down large, dangerous animals regularly. Their prey included bison, horses, young mammoths, ground sloths, and other large herbivores. Europe and Asia had their own giant cats. Cave lions were larger than modern African lions, possibly the largest cats ever to exist. They lived across Eurasia during the Ice Age, from Spain to Alaska. Despite the name, they didn't actually live primarily in caves. That name comes from the fact that their fossils are often found in caves, probably because they used caves as dens or because their bones accumulated there through natural processes. But they were open country hunters, taking down large prey on the grasslands and tundra. We even have cave painting created by early humans showing cave lions. These ancient artists drew lions with accuracy that suggest close observation. Some paintings show details like mane structure and coat patterns. Interestingly, male cave lions in the paintings often don't have manes like modern male lions do. This matches what we know from fossils. Cave lions probably had minimal manes, possibly because heavy manes would be a disadvantage in cold climates where they could collect ice. Then there were the bears. Cave bears were huge, some individuals reaching weights of 500 kilograms. Despite their intimidating size, most evidence suggests they were primarily herbivorous. Isotope analysis of their bones shows they ate mainly plants, but they weren't harmless. A 500 kilogram animal is dangerous regardless of diet, especially if startled or protecting young. Cave bears hibernated in caves during winter, and that's where we find most of their fossils. Some caves in Europe contain the bones of hundreds or even thousands of individual cave bears, representing generations that use the same hibernation sites. Interestingly, cave bears went extinct earlier than many other megafauna, around 27,000 to 24,000 years ago. The reasons aren't entirely clear, but it might relate to competition with humans for cave space, or changes in vegetation affecting their food supply. North America had its own terrifying bear. The giant short-faced bear might have been the largest mammalian land predator ever. These bears stood over 3 meters tall when rearing up on their hind legs and may have weighed up to 800 kilograms. Their legs were proportionally longer than modern bears, suggesting they were built for running across open terrain rather than climbing or digging. There's debate about whether giant short-faced bears were active predators or primarily scavengers. Their teeth and jaw structure could handle both hunting and scavenging. Their long legs would allow them to cover vast territories looking for carrion or hunting opportunities. They might have been opportunistic, hunting when possible and scavenging when available. Regardless, you definitely wouldn't want to encounter one. Wolves were incredibly successful Ice Age predators. Dire wolves in the Americas were larger and more heavily built than modern grey wolves, with more powerful jaws designed for crushing bone. Like modern wolves, they probably hunted in packs, using cooperation to bring down prey much larger than themselves. La Brea tar pits have yielded more dire wolf fossils than any other carnivore, over 4,000 individuals. That's an astonishing number, suggesting dire wolves were extremely abundant. Pack hunting allowed them to take down formidable prey through coordinated attacks, surround the animal, attack from multiple directions, wear it down through repeated bites. Eventually, blood loss and exhaustion would cause the prey to collapse. Then the pack could feed. Fossil evidence shows many dire wolves had healed injuries, broken bones that had mended during life. This suggests they had social structures where pack members would care for injured individuals, sharing food so the injured wolf could survive and recover. That's sophisticated social behaviour requiring communication and cooperation. Even birds got in on the megafauna action. Teratorns were some of the largest flying birds ever, with wingspans exceeding 3.5 meters. They probably soared on thermals like modern condors, searching for carrion across vast distances. With their enormous size, they could access food that smaller scavengers couldn't reach and could defend carcasses from competitors. Let's travel back in time to 20,000 years ago. This moment represents the last glacial maximum. the point when the 100,000-year cycle reached its coldest extreme. Ice sheets at their absolute peak. The world transformed into something that would be barely recognizable if you could somehow be transported there. Standing in what would one day become central Canada, you wouldn't see forests or lakes or cities. You'd see ice extending in every direction to the horizon and beyond. The Laurentide ice sheet covered virtually all of Canada and extended south into the northern United States, reaching as far as modern-day New York and Seattle. In some places, this ice was more than 3 kilometers thick. 3 kilometers? That's taller than the world's tallest building stacked on top of itself more than 3 times. Except instead of steel and glass, it's solid, frozen water pressing down with unimaginable weight. The pressure was so immense that it actually deformed the Earth's crust underneath. The solid rock of the continental plate was pushed downward into the more plastic mantle below. Imagine pressing your thumb into soft clay. The clay deforms under pressure. The same thing happened to Earth's crust, except the clay was solid rock, and the thumb was a mountain of ice kilometers thick. Europe had its own massive ice sheet. The Fennoscandian ice sheet blanketed Scandinavia, Finland, the Baltic region, parts of Britain, and extended into northern Russia. Between these two enormous ice masses, you're looking at roughly 15 million cubic kilometers of ice sitting on land. To put that in perspective, that's almost incomprehensible. If you took all that ice and somehow spread it evenly over the entire land surface of Earth, every continent and island, it would create a layer about 100 meters deep everywhere. The amount of water locked up in these ice sheets was staggering. And remember, that water had to come from somewhere. It came from the oceans. As water evaporated from ocean surfaces and fell as snow on the growing ice sheets, it got trapped on land instead of returning to the sea through rivers. The result was a dramatic drop in global sea level. Not a few meters, not even a few dozen meters. Sea levels dropped by approximately 120 meters. Stand at a modern beach and look out at the ocean. Now imagine the water level dropping down the height of a 40-story building. That's how much lower the oceans were. The exposed continental shelves created vast new land areas. The English Channel didn't exist as a body of water. Britain was connected to mainland Europe by a broad plain. You could walk from London to Paris without ever seeing water deeper than a puddle. The North Sea was largely dry land, with rivers running through it. The Persian Gulf, which today is a significant body of water separating Saudi Arabia from Iran, was a river valley. The Tigris and Euphrates rivers merged and flowed down this valley to reach the ocean much farther south. Indonesia presents one of the most dramatic transformations. Today it's an archipelago of thousands of separate islands. During the last glacial maximum, most of these islands were connected as a single landmass called Sundaland, joined to mainland Southeast Asia. You could walk from Thailand to Borneo to Java without crossing any significant water. Australia, New Guinea and Tasmania formed a single continent called Sahul. The shallow seas separating them today were dry land. Aboriginal Australians could walk from what's now Tasmania to northern New Guinea, a distance of thousands of kilometres without ever needing a boat. Between Asia and North America, the Bering Strait was dry land. This connection, called Beringia, wasn't just a narrow bridge. It was a vast region, perhaps 1,000 kilometres wide from north to south, with its own unique ecosystem. Mammoths, bison, and eventually humans crossed this land connection, moving between continents. The world map was genuinely different. Continents had different shapes. Major islands didn't exist. Straits and channels were dry valleys. If you showed a glacial maximum map to someone familiar only with modern geography, they'd barely recognise Earth. But the transformation went beyond just geography and ice coverage. The climate itself operated differently in ways that affected every aspect of the environment. It wasn't just colder, it was also dramatically drier. With so much water locked up as ice on land, and with colder ocean temperatures reducing evaporation rates, there was simply less moisture in the atmosphere. Less moisture meant less rainfall and snowfall outside the ice sheet regions. deserts expanded. The Sahara Desert, already large today, was even bigger during glacial periods. The Amazon rainforest, that vast green lung of South America, was much smaller and drier. Large areas that are dense forest today were probably savanna or dry woodland during glacial times. Grasslands and steppes covered enormous areas that are forested today. The mammoth steppe was the dominant ecosystem across huge stretches of the northern hemisphere. This unique grassland ecosystem supported incredible densities of large herbivores. Cold, dry, windy conditions prevailed across much of the planet. The ice sheets acted like giant refrigerators, constantly generating cold, dense air. This cold air would flow off the ice in powerful winds, sweeping across the landscape. These katabatic winds, as they're called, were fierce and unrelenting. The winds picked up dust and silt from exposed ground and carried it vast distances. Some regions accumulated deposits of this wind-blown sediment, called loess, that are over 100 metres thick. That's not a misprint. 100 metres of dust accumulated over the glacial periods. The dust storms must have been extraordinary events, darkening the skies for days at a time, reducing visibility to nearly zero, coating everything in fine sediment. Imagine standing on the Mammoth Steppe during one of these dust storms, the wind howling, carrying stinging particles of silt. The sun reduced to a dim orange disk barely visible through the dust. The air so dry it makes your throat roar. Temperatures well below freezing even in summer. This was the world at peak glaciation. Harsh, brutal, unforgiving. And yet, life didn't just cling to existence in this world. It flourished. The megafauna we've been discussing weren't struggling to survive. They were thriving, existing in enormous numbers across vast territories. The Mammoth Steppe supported herds of mammoths, bison, horses, and other large herbivores that probably rivaled or exceeded the density of large animals in modern African savannas. Recent studies using ancient DNA extracted from sediment cores have revealed just how many animals were out there. By sampling DNA from soil that's been frozen since glacial times, scientists can identify which species were present even without finding actual bones. These studies show that Ice Age grassland supported incredibly diverse and abundant megafaunal communities. This frozen, dusty, wind-scoured planet was home to some of the most magnificent ecosystems Earth has ever produced. The last glacial maximum represents an extreme state, but it's not a permanent one. The orbital cycles were already shifting, moving toward a configuration that would favour warming. Within a few thousand years, those massive ice sheets would begin their collapse. Sea levels would rise again, temperatures would warm, and most of the megafauna that had thrived for hundreds of thousands of years through multiple cycles would face their greatest challenge yet. The Mammoth Steppe deserves deeper attention because it was unlike any ecosystem existing today. Modern Earth doesn't have anything quite like it. The closest analogue might be the grasslands of Central Asia or the Arctic tundra, but neither captures the unique character of this vanished landscape. It was called a steppe because it was dominated by grasses, but not the tall grasses you might imagine in African savannas or American prairies. These were tough, cold-adapted grasses mixed with sedges, herbs and low shrubs. Vegetation that could handle extreme conditions, long, dark, frigid winters, short, cool summers, dry conditions year-round, strong winds constantly, permafrost just below the surface preventing deep root growth. Despite these harsh conditions, the Mammoth Steppe was remarkably productive. The key was the growing season. During summer, the sun barely set in high northern latitudes, 20 hours of daylight or more. Plants could photosynthesize almost continuously for weeks on end. This created a pulse of growth that produced enough vegetation to support huge populations of herbivores. The herbivore community was diverse beyond anything on modern grasslands. Woolly mammoths were the most visible, but they shared the landscape with many other species. Woolly rhinoceros grazed alongside them. Several species of horses adapted to cold conditions. Bison, though not as large as modern American bison, were present in vast numbers. Reindeer called caribou in North America migrated in enormous herds. Musk oxen, those shaky survivors that still exist in the Arctic today, were common. Saiga antelope with their distinctive bulbous noses. Each species had slightly different feeding preferences, which reduced direct competition. Mammoths were bulk grazers. They ate large quantities of whatever vegetation was available, using their trunks to grasp plants and their molars to grind them up. They weren't particularly selective. Woolly rhinoceros were more choosy, using their horns to dig through snow to find specific preferred plants. Horses grazed closer to the ground than mammoths, eating shorter vegetation. Bison focused on certain types of grasses. Reindeer supplemented grass with lichens, especially in winter. This diversity of feeding strategies allowed multiple large herbivore species to coexist without depleting the food supply. It's similar to how African savannas support elephants, rhinos, zebras, wildebeest, and many antelope species all grazing in the same area without outcompeting each other. The herbivores weren't just consumers of vegetation. They were ecosystem engineers actively shaping the landscape. Mammoths, in particular, had enormous impacts. They knocked down trees and shrubs, preventing woody vegetation from encroaching on grasslands. Their trampling broke up the soil surface. Their dung distributed nutrients and plant seeds across vast distances. A single mammoth produced hundreds of kilograms of dung per day, all of it rich in partially digested plant material and nutrients. Multiply that by millions of mammoths across the steppe, and you get a massive nutrient redistribution system. This maintained the grassland character of the ecosystem. Without large herbivores constantly suppressing tree and shrub growth, many areas of the mammoth steppe would probably have transitioned to forest or dense shrubland. The animals kept it open. This is called a grazing lawn feedback system. Large herbivores maintain grasslands. Grasslands support large herbivores. It's a self-reinforcing cycle. Predators were a crucial part of the system. Those saber-toothed cats, cave lions, dire wolves, and other carnivores we discussed earlier all depended on the herbivore populations. Predation kept herbivore numbers in check, preventing them from overgrazing and destroying their own food supply. Scavengers played important roles too. Once predators made a kill, they might feed for hours or even days on a large carcass. But they couldn't consume everything. Wolves, foxes, ravens, and other scavengers would move in to claim the remains. Even the bones would eventually be gnawed by rodents seeking calcium. Nothing went to waste. The seasonal cycle on the mammoth steppe would have been dramatic. Winter was a time of survival. Temperatures could plunge to minus 40 degrees or colder. Snow covered the vegetation. Herbivores had to dig through snow to find food or survive on whatever woody browse they could reach. Many species migrated, following areas with less snow or accessible food. Predators faced lean times, surviving on whatever prey they could catch or scavenge. Spring brought the thaw. Melting snow created temporary wetlands and streams. Migrating animals returned. Plants began their explosive growth. This was calving season for many herbivores. Mammoths, horses, and bison gave birth to young that would grow quickly during the abundant summer months. Predators found ample hunting opportunities, targeting vulnerable young animals. Summer was the time of plenty, continuous daylight, lush vegetation. Animals feeding constantly to build up fat reserves for the coming winter. This was also mating season for many species. Massive bull mammoths would compete for females, clashing tusks in dominance battles. Male deer and other species displayed their antlers and fought for breeding rights. Autumn meant preparation. Animals needed to accumulate as much fat as possible before winter returned. Some species migrated to winter ranges. Others grew thicker winter coats. The cycle would begin again. Archaeological and paleontological evidence shows us that these ecosystems were stable for hundreds of thousands of years. The same basic pattern repeated through multiple glacial cycles. Ice sheets would advance. The mammoth steppe would establish itself south of the ice. Megafauna would thrive. Ice sheets would retreat. Forests would expand. The steppe would shrink, but not disappear. Ice sheets would advance again. The steppe would re-expand. The species involved were well adapted to this rhythm. They'd evolved through hundreds of these cycles. Their populations would expand and contract with the grasslands, but they persisted. This had been the pattern for longer than our species existed. But patterns, even ancient ones, can break. And the pattern was about to break in a way that would doom most of these magnificent creatures. Humans weren't absent from this Ice Age world, but when we talk about humans during the glacial periods, we need to include more than just our own species. Neanderthals were already living in Europe and parts of Asia long before modern humans arrived. They'd been there for hundreds of thousands of years, surviving through multiple glacial cycles. These weren't primitive evolutionary dead ends. They were sophisticated, successful humans who had mastered life in Ice Age conditions. Let's correct some misconceptions right away. The image of Neanderthals as brutish cavemen grunting and clubbing things is completely wrong. It's a caricature based on outdated 19th century ideas. Modern research paints a radically different picture. Neanderthals were intelligent, culturally complex, technologically capable humans who thrived in one of the most challenging environments Earth has ever produced. Their physical adaptations to cold were remarkable. Neanderthals were shorter and stockier than modern humans, with barrel chests, thick bones and heavily muscled bodies. The average male stood about 160 centimetres tall. They weren't tall, but they were incredibly strong. Their bones show massive muscle attachment sites indicating strength that would exceed most modern humans. This body build wasn't random. It was adaptation to cold, following the same Bergmann's rule we discussed for Megafauna. Shorter, stockier bodies with lower surface area to volume ratios lose heat more slowly. In frigid conditions, this body shape is advantageous. It's why modern populations native to extremely cold regions, like some Arctic peoples, tend towards stockier builds. Neanderthal faces had distinctive features that also served functional purposes. Large noses with wide nasal passages. These weren't just for looks. Those big nasal cavities acted as heat exchangers, warming and humidifying frigid air before it reached the lungs. Same adaptation we see in woolly mammoths and other Ice Age mammals. Repeatedly breathing extremely cold, dry air damages respiratory tissues. Neanderthals evolved built-in protection. Their skulls had other interesting features. Large brain cases housing brains that were actually slightly larger on average than modern human brains. Pronounced brow ridges and robust facial features. These physical characteristics made them look different from us, but they don't indicate lesser intelligence. Brain size and intelligence don't correlate simply. Neanderthals were smart. Their technology proves it. Neanderthals made sophisticated stone tools using a technique called levallois. This method requires extensive planning. You prepare a stone core carefully through multiple steps. Then you strike it precisely to detach a finished flake of predetermined shape. It's like sculpting. You have to envision the final product before you begin, and execute a complex sequence of actions to achieve it. That requires abstract thinking and planning ability. They also made wooden spears with a remarkable craftsmanship. Several spears have been found preserved in peat bogs in Germany. These weren't just sharpened sticks. They were carefully shaped, balanced, with tips hardened by fire to make them more durable. These are engineered weapons. Analysis shows they were weighted properly for throwing, with the centre of balance positioned to maximise flight stability. Neanderthals hunted with these weapons, and they hunted dangerous animals. Fossil sites show Neanderthal remains mixed with bones of bison, reindeer, wild horses, woolly rhinoceros, and even mammoth. The bones have cut marks from stone tools made while the meat was fresh. These weren't scavenged carcasses. Neanderthals were actively hunting large, dangerous prey. Successfully bringing down a woolly rhinoceros or a bison requires skill, coordination, and bravery. These animals can kill you easily if the hunt goes wrong, but Neanderthals did it regularly enough to leave extensive archaeological evidence. Fire technology was sophisticated. They didn't just maintain natural fires. They could create fire deliberately using techniques like striking pyrite against flint to generate sparks. They used fire for warmth, cooking, hardening wooden spear points, and even making complex adhesives. Archaeologists have found Neanderthal tools with birch bark tar used to attach stone points to wooden handles. Making birch bark tar requires heating birch bark in the absence of oxygen at specific temperatures. This is a multi-step chemical process. You can't stumble into discovering it. You need understanding of materials and controlled application of heat. Neanderthals figured this out tens of thousands of years ago. Their cultural life was rich. They made ornamental objects. Pierced shells and eagle talons have been found at Neanderthal sites, apparently strung together as jewellery or decorative items. They used pigments like ochre, possibly for body painting or decorating objects. Most significantly, they buried their dead. Multiple Neanderthal burial sites have been found across Europe and the Middle East. These aren't accidental deposits of bones. These are deliberate burials where bodies were placed in specific positions, sometimes in graves dug specifically for that purpose. Some burials show evidence of grave goods, objects placed with the deceased. The famous Shanidar cave in Iraq has Neanderthal burials that some researchers initially thought included flowers, though that interpretation is now debated. Regardless of flowers, the deliberate burial itself is significant. It indicates these people thought about death, possibly had beliefs about what happens after death, and cared enough about their dead to conduct rituals. That's deeply human behaviour. Recent discoveries show Neanderthals even created art. In caves in Spain, abstract geometric patterns and hand stencils have been found that date to periods when only Neanderthals occupied the region. These are among the earliest known examples of cave art. We also know from genetic evidence that Neanderthals and modern humans interbred. When modern humans expanded into Europe and Asia, starting around 50,000 years ago, they encountered Neanderthals. And they didn't just fight or avoid each other. They had children together. Those hybrid children survived, had their own children, and some of their DNA persists today. If you have European or Asian ancestry, you probably carry 1 to 2% Neanderthal DNA. That percentage seems small, but it represents thousands of genetic variants. Some of those variants affect immune function, helping us fight diseases. Others affect skin and hair traits. Some influence metabolism. Neanderthal genes are literally part of us. So if Neanderthals were so capable, so well adapted, so successful, why did they disappear? They survived for hundreds of thousands of years through multiple glacial cycles. Then around 40,000 years ago they went extinct. The last known Neanderthal populations disappeared from their final refuges in southern Europe. What happened? This question has generated decades of debate. We'll explore it more later, but the short answer is probably competition with modern humans combined with changing climate conditions. Modern humans brought new technologies, different social structures, possibly advantages in language or cognition that were subtle but significant. But Neanderthals weren't swept aside immediately. They coexisted with modern humans for thousands of years. The transition wasn't instantaneous replacement. It was gradual decline over millennia. What's clear is that both Neanderthals and modern humans were capable of surviving Ice Age conditions through intelligence, technology, and cultural adaptation. We weren't just passive inhabitants of the Ice Age world. We were active participants, shaping our environment and hunting the same megafauna that dominated the landscape. While Neanderthals dominated Europe and parts of Asia, another human species was evolving in Africa. Homo sapiens, anatomically modern humans, emerged around 300,000 years ago. For most of that time, we stayed in Africa and the Middle East. But starting around 70 to 80,000 years ago, modern humans began expanding outward. By 50,000 years ago, we'd reached Australia. By 45,000 years ago, we were in Europe, encountering Neanderthals. By 15,000 to 20,000 years ago, we'd entered the Americas. Within a remarkably short time, modern humans had spread to every continent except Antarctica. What made this expansion possible? Technology and innovation. Modern humans developed new tools, new hunting methods, new ways of organising socially, and new forms of symbolic expression. These innovations gave us advantages that allowed us to thrive in diverse environments, including the harsh Ice Age world. Let's talk about weapons first. Early humans used thrusting spears, which required getting close to prey, dangerous when hunting mammoths or bison. Then came a revolutionary invention called the atlatl, or spear thrower. This is a stick with a hook or socket at one end that holds the back of a spear. You grip the atlatl and throw, using it as a lever arm. The physics are beautiful. The atlatl effectively extends your arm length, allowing you to impart much more energy to the spear. You can throw farther, harder, and more accurately. Suddenly you can attack dangerous prey from 20 or 30 meters away instead of close range. The atlatl appears in the archaeological record around 30,000 years ago in Europe and spread widely. It remained the primary hunting weapon for thousands of years. Later, probably between 20 and 30,000 years ago in some regions, humans invented an even better weapon, the bow and arrow. This was transformational. Arrows fly faster than atlatl darts. They're more accurate. You can carry more ammunition. You can shoot rapidly, releasing multiple arrows in quick succession. And bows allowed hunting of smaller, faster animals that were difficult to hit with spears. The bow might be one of humanity's most important technological inventions. It fundamentally changed hunting effectiveness and also created a powerful weapon for warfare between human groups. Hunting strategies became more sophisticated. Archaeological sites show evidence of coordinated group hunts. Multiple individuals working together to drive herds of animals toward cliffs or into constructed traps. There are sites with the bones of hundreds of bison that were stampeded off cliffs, then butchered systematically. This requires serious coordination. Scouts to locate herds, drivers to stampede them in the right direction, people positioned to finish off injured animals, butchers to process the carcasses. It's complex social behaviour requiring communication, planning and defined roles. But humans weren't just hunting terrestrial animals. We also turned increasingly to aquatic resources. Fishing technology developed. Harpoons carved from bone or antler for spearing fish. Fish hooks made from bone. Evidence of nets woven from plant fibres. Coastal populations exploited shellfish, fish, seals, and other marine resources intensively. Shell middens, enormous deposits of discarded shells, mark long-term coastal occupation sites. Some middens are tens of meters thick, representing thousands of years of shellfish harvesting. Aquatic resources provided reliable food with less risk than hunting megafauna. You're not likely to be killed by a salmon. Clothing technology advanced dramatically. Around 40,000 years ago, bone needles appear in the archaeological record. These aren't crude awls for punching holes. These are fine needles with eyes for thread, used for sewing. This indicates creation of fitted clothing with sleeves, closures, carefully joined seams. Fitted clothing is far superior to simply wrapping hides around yourself. It traps warm air more effectively. It allows freedom of movement. It protects better against wind and moisture. Sewn clothing probably allowed humans to survive in colder regions that would otherwise be uninhabitable. Shelter became more sophisticated. In regions with abundant wood, people built substantial wooden structures. In treeless regions, they improvised. Some of the most impressive are the mammoth bone houses found in Ukraine and Russia. These are dwelling structures with frameworks built from mammoth bones and tusks, covered with hides. Some use bones from dozens of individual mammoths, representing thousands of kilograms of material. These weren't temporary shelters. They were substantial houses where people lived for extended periods. The effort to construct them was enormous, collecting all those bones, transporting them to the site, arranging them into stable structures, securing the hide coverings. These were major construction projects, indicating long-term settlement rather than nomadic wandering. Social organisation was clearly complex. The large-scale hunts required coordination. The construction projects required cooperation. Long-distance trade networks existed, proven by finding raw materials hundreds of kilometres from their sources. Stone for tools, shells for ornaments, amber, ochre pigments. These materials were traded over vast distances, indicating networks of social connections and information exchange. And humans were creating art. Lots of art. The cave paintings are justly famous. Lascaux in France, Chauvet Cave, Altamira in Spain. These aren't crude stick figures. They're sophisticated artwork showing animals in motion, using natural cave wall contours for three-dimensional effects, mixing pigments for different colours, employing techniques like shading and perspective. The artists clearly spent extensive time observing these animals to depict them so accurately. Some paintings show remarkable details. A woolly rhinoceros with its characteristic fur clearly indicated. Mammoths with their domed heads and long tusks. Horses in motion. Bison charging. These images were created by people who saw these animals alive, who watched them move, who understood their anatomy. But it wasn't just paintings. People carved figurines from ivory, bone and stone. The Venus figurines, stylized female forms, are found across Europe. Some have elaborate details like hairstyles or clothing carved into them. People made musical instruments, flutes carved from bird bones or mammoth ivory. These produce clear musical notes. Ice Age humans were making music. They created elaborate burials. The burial of children at Singir in Russia included thousands of ivory beads sewn onto clothing. Researchers estimated it would have taken someone working full-time several months to create all those beads. Someone invested enormous labour to create burial garments for children. That speaks to deep emotional bonds and symbolic thinking. Why did humans create art? Probably multiple reasons. Some cave art might relate to hunting, magic, or spiritual rituals. Some figurines might be religious symbols. Some art was probably aesthetic, created for beauty or pleasure. Some might relate to social bonding or storytelling. Art indicates that Ice Age humans had rich symbolic lives, abstract thinking, spiritual beliefs and cultural traditions. They weren't just surviving, they were creating meaning and beauty in a harsh world. This combination of technological innovation, social cooperation, and symbolic culture made modern humans extraordinarily adaptable. We could survive in environments from tropical rainforests to Arctic tundra. We could exploit diverse food sources. We could modify our environment to suit our needs. And this adaptability would prove crucial as the Ice Age world entered its final transformation. Around 19,000 years ago, something shifted. The orbital cycles that had maintained frigid conditions were moving into a new configuration. Northern Hemisphere summers were receiving more solar radiation. The ice sheets that had dominated the planet for over 100,000 years began to respond. Not dramatically at first. Ice sheets don't melt quickly. They're massive, containing enormous thermal inertia. It takes sustained warming over centuries to make them retreat significantly. But the process had begun. Summer melting exceeded winter accumulation. The balance tipped. Instead of growing, the ice sheet started shrinking. Meltwater began trickling, then streaming, then pouring off the ice. Rivers swollen with glacial melt-carved channels through the landscape. Lakes formed at the ice margins where meltwater pooled. Sea levels, which had been stable at their low point for thousands of years, began rising. This wasn't a smooth, gradual process. Deglaciation happens in pulses, periods of rapid change interspersed with relative stability. One of the most dramatic pulses occurred around 14,600 years ago. It's called Meltwater Pulse 1A. During this event, sea levels rose approximately 20 metres in less than 500 years. 20 metres. That's enough to flood vast coastal areas, submerge land bridges, and completely transform coastlines. In geological terms, 500 years is essentially instantaneous. That's how fast massive sections of the ice sheets collapsed. Where did all that water come from so quickly? Parts of the great ice sheets became unstable and disintegrated. Imagine sections of ice kilometres thick breaking apart and sliding into the ocean. The resulting icebergs would have been staggering in size. The oceans during this period must have been crowded with enormous ice islands slowly melting as they drifted. For the megafauna and human populations living near coasts, this would have been catastrophic. The places where they lived, hunted and foraged, were disappearing under rising water. Entire landscapes vanished. As the ice retreated, it left behind a transformed terrain. The land that had been compressed under kilometres of ice for thousands of years began slowly rebounding, rising up as the weight was removed. This process, called isostatic rebound, continues today in regions like Scandinavia and Canada. The landscape was raw and bare, scraped clean by the ice, covered in glacial debris, dotted with countless lakes formed in depressions carved by the ice. It must have looked alien and barren. But plants are remarkably quick to colonize new terrain. Seeds blown by wind or carried by animals found purchase in the glacial till. Mosses and lichens established themselves on bare rock. Grasses followed, shrubs, eventually trees. The warming continued for several thousand years. By around 14,700 years ago, temperatures had risen substantially. Ice sheets were in full retreat. Things seemed to be heading steadily toward interglacial conditions. The world was transforming from ice age to something warmer and wetter. Then, suddenly, everything reversed. Around 12,900 years ago, temperatures crashed. In Greenland, ice core records show temperature drops of approximately 15 degrees Celsius in just a few decades. Some evidence suggests it could have happened even faster, possibly in as little as 10 to 20 years. The North Atlantic region was plunged back into near glacial conditions. This cold snap lasted over 1,000 years, from about 12,900 to 11,700 years ago. It's called the Younger Dryas, named after an Arctic wildflower that spread during this cold period. The Younger Dryas is one of the most dramatic climate events in recent Earth history. A sudden reversal in the middle of deglaciation. Temperatures that had been warming for thousands of years suddenly plummeted back to near Ice Age levels within a generation. Why did this happen? The leading explanation involves a catastrophic flood. As the North American ice sheet melted, enormous quantities of meltwater accumulated in glacial lakes dammed by the ice itself. The largest was Lake Agassiz, which at its peak was bigger than all the modern Great Lakes combined. Imagine a freshwater sea the size of a significant ocean basin, held back only by walls of ice. When those ice dams failed, which geological evidence shows they did multiple times, the results were spectacular. Unimaginable volumes of water burst through the ice barriers and flooded toward the ocean. We're talking about enough water to raise global sea levels by meters, released in a geologically instant time frame. This massive freshwater dump disrupted ocean circulation patterns in the North Atlantic. There's a crucial ocean current system called the Atlantic Meridional Overturning Circulation. You might have heard it called the Gulf Stream, though that's not quite accurate. The Gulf Stream is one component. The full system is like a conveyor belt. Warm surface water flows northward, carrying heat from the tropics toward the Arctic. As this water reaches high latitudes near Greenland, it cools down, becomes denser, and sinks to the deep ocean. Then it flows southward at depth, completing the circuit. This circulation transports enormous amounts of heat northward, warming the northern hemisphere significantly. Western Europe is much warmer than it would otherwise be at its latitude thanks to this heat transport. But the system has a vulnerability. It depends on differences in water density to drive the sinking in the North Atlantic. Salty water is denser than fresh water. When you dump massive amounts of fresh water into the North Atlantic, it floats on top of the denser salty water and prevents the normal sinking. The conveyor belt slows down or stops. When it stops, the Northern Hemisphere stops receiving that massive heat transport from the tropics. Temperatures crash. You can shift from warm conditions to near glacial cold within years. That's what apparently happened during the Younger Dryas. Catastrophic meltwater flooding shut down the ocean circulation. The resulting cold snap lasted over 1,000 years until the system restarted. The effects weren't limited to the North Atlantic region. The Younger Dryas affected climate patterns globally. Some regions got drier, others got wetter, temperature patterns shifted. This had profound impacts on ecosystems everywhere. For megafauna that were already stressed by habitat changes as forests expanded and grasslands shrank, the Younger Dryas added another shock. Suddenly it was cold again, but the landscape had changed. The mammoth steppe that had sustained them was fragmenting. For human societies, the Younger Dryas was also transformative. In the Middle East, this is precisely when agriculture first appears in the archaeological record. Some researchers think the climate stress of the Younger Dryas pushed hunter-gatherer groups to start deliberately cultivating plants. When wild food resources become unreliable, you need alternatives. Farming emerged as a solution. If that connection is real, then this climate event triggered by the 100,000-year cycle, transitioning from glacial to interglacial, literally set human civilization on a new trajectory. The Younger Dryas ended as abruptly as it began. Around 11,700 years ago, temperatures spiked upward again. In some regions, the warming happened over just a decade or two, 10 degrees Celsius or more of a warming in 10 years. That's almost incomprehensibly fast for natural climate change. The ocean circulation restarted, heat flooded northward again. Ice sheets resumed their collapse, and this time there would be no reversal. The transition to full interglacial conditions was complete. We call this moment the beginning of the Holocene, our current geological epoch. It marks the end of the last glacial period. For the megafauna, this rapid warming and ecosystem transformation would prove catastrophic. The creatures that had thrived for hundreds of thousands of years through multiple cycles were about to face their ultimate test. 11,700 years ago marked the beginning of the Holocene. Temperatures stabilized at levels similar to today. The Younger Dryas cold snap was over. The world was warm and getting warmer. Ice sheets continued their retreat. Forests expanded massively, spreading across areas that had been grassland or tundra for tens of thousands of years. The mammoth steppe, that unique ecosystem that had supported incredible megafaunal diversity, was disappearing, transforming into forest, wetland, and a different kind of tundra. For animals adapted to cold, dry grasslands, this was a crisis, and the extinctions came fast. In North America, most megafauna disappeared between approximately 13,000 and 11,000 years ago. Mammoths, gone. Mastodons, gone. Horses, extinct in the Americas. Camels, which had actually evolved in North America, vanished from the continent. Giant ground sloths, all species extinct. Glyptodonts, extinct. Saber-toothed cats, extinct. Dire wolves, extinct. Giant short-faced bears, extinct. American lions, extinct. The list goes on. We're talking about roughly 70 to 80% of large mammal species in North America disappearing within just a few thousand years. That's a mass extinction event. It's called the Quaternary Extinction Event, and it devastated the megafaunal communities that had dominated the continent. Europe experienced similar losses, though the timing varies by species. Woolly mammoths disappeared from most of their range. They hung on in a few isolated refuges, which we'll discuss shortly, but across the vast territories they once roamed, they vanished. Woolly rhinoceros went extinct completely. Cave lions, gone. Giant deer with their spectacular antlers, extinct. Cave bears had already disappeared earlier, but many other large species followed. South America lost its unique megafauna in a similar time frame. All the giant ground sloth species, extinct, every single one. Glyptodonts, gone entirely. The native horses and camels that had lived there, extinct. Toxodons, those bizarre hippo-like mammals, gone. Macrauchenia, which looked like strange combinations of camels and elephants, extinct. Giant armadillos, extinct. The giant anteaters and giant capybaras survived, but most of the spectacular South American megafauna disappeared. Australia had already lost most of its megafauna earlier, between about 50,000 and 40,000 years ago. Giant wombats, enormous kangaroos, massive flightless birds, a marsupial lion, all disappeared. The timing in Australia is significant because it coincides more with human arrival than with the deglaciation, which adds important evidence to the debate about what caused these extinctions. So what killed them? This question has generated intense debate for decades, and honestly, it's still not completely resolved. There are two main hypotheses, climate change and human hunting, and the truth almost certainly involves both, with their relative importance varying by region and species. The climate change hypothesis argues that rapid warming and ecosystem transformation was more than these animals could handle. Megafauna had evolved over hundreds of thousands of years for cold, dry, open habitats. When those habitats disappeared in just a few thousand years, adaptation couldn't keep pace. As forests expanded and grassland shrank, megafauna populations became fragmented into smaller and smaller patches of suitable habitat. Small, isolated populations face multiple problems. Inbreeding reduces genetic diversity and fitness. Random environmental fluctuations can wipe out small groups. Disease spreads more easily in confined populations. This creates what ecologists call an extinction vortex. Declining populations face compounding threats that make recovery impossible. There's good evidence for climate being a major factor. The extinctions happened during a period of incredibly rapid climate change. The Younger Dryas alone would have been enormously disruptive, and then the subsequent warming was even faster. Species adapted to cold climates suffered most. Woolly mammoths and woolly rhinoceros, perfectly adapted to Ice Age conditions, went extinct. Meanwhile, species adapted to forests or warmer climates generally survived. This pattern strongly suggests climate played a crucial role. But here's a complication. Megafauna had survived previous deglaciations. The 100,000-year cycle means there were multiple transitions from glacial to interglacial conditions over the past few million years. If megafauna survived those earlier transitions, why not this one? That's where the human hunting hypothesis becomes important. Modern humans had spread across most of the world by the end of the last ice age. Human populations were larger than in previous interglacials. Our technology was more advanced. We had atlatls, bows and arrows, coordinated hunting strategies, fire for landscape management. We were more effective hunters than any previous human species, and critically, in many regions, megafauna had little or no evolutionary experience with human hunters. In the Americas, humans arrived relatively recently, probably within the past 20,000 years. The megafauna there had never encountered human hunters before. They were naive prey. We see this pattern repeatedly in history. When humans first reach oceanic islands with no previous human presence, the native birds and mammals show no fear. They walk right up to humans. They're easily caught and often driven extinct within decades or centuries. The same might have happened with Ice Age megafauna in regions where humans arrive for the first time. And here's the crucial thing about hunting megafauna. You don't need intensive hunting to drive them extinct. These animals reproduce slowly. A female mammoth might have a calf every 5 years. Mammoths don't reach sexual maturity until their teens, if you kill even a small percentage of the population each year, especially reproductive females. You can drive the population into irreversible decline. Mathematical models show that very low-intensity hunting, removing just a few percent of the population annually, can cause extinction of large-bodied animals over centuries to millennia. You don't need to hunt them relentlessly. Just modest, sustained hunting pressure, combined with other stresses, is enough. And we know humans hunted megafauna. The evidence is undeniable. We've found butchered mammoth bones at human sites with clear cut marks from stone tools, spear points embedded in mammoth ribs, kill sites where multiple animals were driven off cliffs or into traps, then systematically butchered. Cave paintings showing hunting scenes. Humans definitely hunted these animals. The question is whether hunting alone could cause extinctions, or whether it was the final stress on populations already struggling with climate change. The timing is suspicious in many regions. In North America, the extinctions coincide almost exactly with the expansion of Clovis culture, a group of humans with particularly effective hunting technology. Clovis points are distinctive spear points found across North America, often at sites with butchered mammoth remains. Within a few thousand years of Clovis people spreading across the continent, the megafauna were gone. That timing is hard to ignore. There's even isotopic evidence suggesting some Clovis people were specialised mammoth hunters. Analysis of a Clovis child burial found that mammoth protein contributed roughly 40% of the maternal diet. That's a lot of mammoth. But we need to be careful not to overinterpret. That's one individual. We can't extrapolate to all Clovis people. And there's debate about whether human populations were large enough to hunt mammoths to extinction across an entire continent. The extinction pattern is also complex. Some species went extinct early, others lasted longer. Mammoths on Wrangel Island in the Arctic Ocean survived until about 4,000 years ago, thousands of years after they disappeared everywhere else. That's during the Bronze Age. Mammoths and pyramids coexisted in time. Why did mammoths survive on that remote island so much longer? Probably because humans didn't reach it until very late. Once humans arrived, the mammoths disappeared quickly. Cave bears went extinct before many other species. Dire wolves disappeared, but grey wolves survived. Bison survived despite being hunted heavily by humans. Why some species made it and others didn't is still being figured out. What seems clear is that the combination of rapid climate change and human pressure was deadly. Climate change stressed populations by fragmenting habitats and reducing food availability. Human hunting prevented struggling populations from recovering. Together, these factors created conditions most megafauna couldn't survive. There may have been other factors too. Diseases, possibly introduced by humans or their domesticated dogs. Indirect effects of human landscape management through fire. The loss of megafauna themselves had cascading ecosystem effects. When mammoths disappeared, the grasslands they maintained transformed into forests, making habitat even less suitable for surviving megafauna. The 100,000-year cycle had sustained these creatures for longer than our species has existed. Through dozens of cycles, megafauna adapted. Populations contracted and expanded with the grasslands, but they persisted. This time was different. This time, when the cycle shifted to warming, there was a new factor. Humans with advanced technology and growing populations. The combination was too much. Within a few thousand years, the Ice Age world of giants was gone forever. The Holocene, our current epoch, brought stability that the late Ice Age lacked. For the past 11,700 years, climate has remained relatively stable compared to the wild fluctuations of the Pleistocene. Sure, there have been variations, warm periods and cool periods, droughts and wet spells, but nothing like the dramatic swings between full glacial and interglacial states, or sudden events like the Younger Dryas. This stability was crucial for human development. For most of human existence, we'd been hunter-gatherers moving with the seasons, following game animals, harvesting wild plants. This lifestyle had sustained us for hundreds of thousands of years. But as the Holocene began, something revolutionary happened. People started farming. Agriculture emerged independently in multiple regions within just a few thousand years of each other. In the Fertile Crescent of the Middle East, people began cultivating wheat and barley around 11,000 to 10,000 years ago. They domesticated sheep and goats. In China, rice and millet cultivation started around 9,000 years ago. In Mesoamerica, maize was domesticated at a similar time. In the Andes, potatoes and quinoa. In New Guinea, taro and bananas. Across the world, humans figured out how to deliberately grow food rather than just gathering what nature provided. Why did agriculture develop when it did? Multiple factors probably contributed. Population growth during the improving climate may have created pressure on wild food resources. The climate stability of the Holocene made farming more predictable and reliable. You could plant in spring with reasonable confidence that summer would arrive and crops would mature. During the wild climate swings of the late Ice Age, that was a risky bet. There's also the hypothesis that megafauna extinction forced humans to find alternative food sources. When the large animals disappeared, people needed substitutes. Plants could fill that gap if cultivated intensively. Agriculture wasn't necessarily an improvement in quality of life, at least not initially. Hunter-gatherers typically had diverse diets with plenty of protein and varied nutrients. Early farmers ate mostly carbohydrates from a few grain crops. Skeletons from early agricultural societies show signs of nutritional stress. More cavities from starchy foods, shorter average height, diseases associated with dietary deficiencies. But agriculture had one overwhelming advantage. It could support far more people per unit of land. A square kilometre of wheat fields can feed dozens or hundreds of people. The same area of wild land might support only a handful of hunter-gatherers. This meant agricultural societies could grow much larger populations. More people meant more workers, more defenders, more inventors. When agricultural and hunter-gatherer societies came into conflict, the farmers usually won through sheer numbers. Agriculture also required permanent settlement. You can't farm effectively while nomadic. You need to stay in one place to plant, tend, protect and harvest crops. So farming led to permanent villages. Those villages grew into towns. Towns eventually became cities. These permanent settlements required new forms of social organisation. Who owns the land? How is surplus food stored and distributed? How do you defend against raiders? How are disputes resolved? Agricultural societies developed hierarchies, leadership structures, laws. They needed ways to track harvests, land ownership, trade. This drove the invention of writing in multiple regions independently. Mesopotamia, Egypt, the Indus Valley, China, Mesoamerica. Humans invented writing to keep records. Writing enabled accumulation of knowledge across generations. It allowed complex administration. It made possible the rise of civilizations. Over a few thousand years, agriculture spread across most of the world where climate allowed it. Sometimes through migration of farming peoples, sometimes through adoption by hunter-gatherers. Either way, most human societies transitioned to farming. The first civilizations emerged in river valleys where agriculture was especially productive. Mesopotamia, between the Tigris and Euphrates, Egypt along the Nile, the Indus Valley, the Yellow River in China. These civilizations developed cities with thousands of inhabitants. Monumental architecture like temples and pyramids, specialized occupations, metalworking, first copper, then bronze, eventually iron, mathematics and astronomy, complex religious systems, art and literature. All of this happened within just a few thousand years of the Ice Age ending. The transformation from small nomadic hunter-gatherer bands to cities with tens of thousands of people is incredibly rapid in evolutionary terms. But while these dramatic changes were happening in some regions, other human societies continued traditional lifestyles successfully. Australia's Aboriginal peoples maintained hunter-gatherer cultures for tens of thousands of years after agriculture was invented elsewhere. Many groups in the Americas remained hunter-gatherers, even while others developed agriculture and cities. In Africa, groups like the San people hunted and gathered successfully into the modern era. Agriculture wasn't inevitable or universal. It was one strategy among many, one that happened to be very successful at supporting large populations and complex societies, but not the only viable way to live. The ecological consequences of the Holocene transition were profound. It wasn't just about megafauna extinction. Entire ecosystems transformed. Forests expanded dramatically. Species adapted to open grasslands had to move, adapt, or disappear. Cold-adapted species retreated northward or to high elevations. Warm-adapted species expanded their ranges. Humans were increasingly shaping these ecosystems, often in ways we didn't fully appreciate until recently. Indigenous peoples worldwide used fire as a landscape management tool, burning regularly to maintain open areas that attracted game or promoted useful plants. This burning had huge effects on vegetation patterns. What we think of as natural wilderness often was actually shaped by thousands of years of human fire management. The loss of megafauna also had cascading effects we're still understanding. Large herbivores like mammoths weren't just eating plants, they were maintaining open habitats, distributing nutrients, creating landscape diversity. When they disappeared, these ecological functions vanished too. Some scientists think forests expanded partly because giant herbivores were no longer suppressing tree growth. There's even a hypothesis that megafauna extinction affected climate. Large herbivores produced methane from digestion. When their populations crashed, methane emissions might have decreased significantly. The transformation from grassland to forests changed how much solar energy the land surface reflected versus absorbed. These effects were probably small compared to orbital forcing, but they weren't zero. The Holocene has been unusually stable, and that stability enabled civilization. But it's important to remember we're still technically in an ice age, just in the warm interglacial phase. Based on past patterns, we should eventually slide back toward glacial conditions. Except there's now a massive complication. Human activity is affecting global climate in ways that might override the natural cycles entirely. We're now approximately 11,700 years into the current interglacial. Based on past interglacial periods, which typically last 10 to 20,000 years, we might be approaching the natural end of warm conditions. The orbital cycles are continuing their slow dance. Eventually they should shift into a configuration favouring ice sheet growth, and Earth should begin sliding back toward glacial conditions. Except that's probably not going to happen, at least not anytime soon, because for the first time in the history of the 100,000-year cycle, one species has gained the power to override it. Us. Human activity is now affecting global climate on a scale that rivals or exceeds the natural orbital forcing. We've increased atmospheric carbon dioxide from the natural interglacial level of about 280 parts per million to over 420 parts per million. That's more than a 50% increase in just 2 centuries. When you look at ice core records extending back 800,000 years, covering multiple glacial cycles, you see carbon dioxide varying between about 180 parts per million during glacials and 280 to 300 parts per million during interglacials, a range of roughly 100 to 120 parts per million, representing the natural variation of the system. We've blown past that range entirely. Current carbon dioxide levels haven't been seen on Earth for at least 3 million years, probably longer. Back in the Pleistocene epoch, when carbon dioxide was last this high, global temperatures were several degrees warmer than today. Sea levels were 15 to 25 meters higher, and the Arctic had forests instead of ice. That's where we're headed if we don't change course. And it's not just carbon dioxide. We've increased methane, nitrous oxide, and other greenhouse gases. We've changed land surfaces through deforestation and agriculture, affecting how much solar energy is reflected versus absorbed. We've altered the nitrogen and carbon cycles. We're conducting a planetary-scale experiment with no control group and no ability to reverse it if things go badly wrong. Some scientists think we've already prevented the next ice age from occurring. The extra greenhouse gases warming the planet make it unlikely that northern hemisphere summers will be cool enough to allow ice sheet formation, even when the orbital cycles shift toward conditions that would normally favour glaciation. We might have cancelled the next 100,000-year cycle entirely. On one level, that sounds good. Nobody wants kilometres of ice covering Canada and Scandinavia again. But the problem is we're not just preventing the next ice age, we're warming the planet way beyond normal interglacial conditions, and we're doing it incredibly fast. The lessons from studying ice age cycles become critically important here. Climate has tipping points. It's not a linear system that responds gradually to forcing. You can push on it for a while, seeing modest changes, then cross a threshold and trigger rapid, dramatic shifts. The Younger Dryas is the perfect example. Gradual warming, then catastrophic flooding, then abrupt reversal within decades. The system flipped states faster than human lifetimes. We're seeing similar threshold behaviour today. Ice sheets don't melt uniformly. They can be stable for long periods, then suddenly accelerate their loss when they cross certain points. The Greenland ice sheet is losing mass at an accelerating rate, currently around 250 billion tonnes per year. Greenland contains enough ice to raise global sea levels by about 7 metres. Even losing a fraction of that over coming centuries would transform coastlines worldwide. And once major melting starts, feedback effects make it difficult to stop. Darker rock, exposed by melting, absorbs more heat. Meltwater lubricates the ice base, making it flow faster. Warm ocean water gets underneath and melts from below. All positive feedbacks amplifying the initial change. The West Antarctic ice sheet is particularly concerning because much of it sits on bedrock below sea level. Warm ocean water is already getting underneath it. Some scientists think major portions might be committed to collapse over coming centuries, even if we stopped warming today. That would mean 3 to 5 metres of sea level rise, hundreds of millions of people displaced, coastal cities transformed or abandoned. Arctic sea ice is declining dramatically. The summer minimum extent has dropped about 40% since satellite measurements began in the 1970s. Some models suggest ice-free Arctic summers within decades. And remember those feedbacks. Ice reflects sunlight. Ocean water absorbs it. Less ice means more heat absorption, more warming, more ice loss. It's self-reinforcing. Permafrost is thawing across the Arctic. This is a huge wild card. Approximately 1,500 billion tonnes of organic carbon is stored in frozen Arctic soils. That's roughly twice as much carbon as currently in the atmosphere. As permafrost thaws, microbes decompose that organic matter, releasing carbon dioxide and methane. Warming causes thawing. Thawing releases greenhouse gases. Greenhouse gases cause more warming. Another positive feedback with the potential to become a runaway process. Ocean circulation patterns are changing. The Atlantic meridional overturning circulation that we discussed in relation to the Younger Dryas shows signs of weakening. If it slows significantly or shuts down, it could cause regional cooling in parts of Europe, even as the globe overall continues warming. Climate is complex and counterintuitive. We're pushing on a system with built-in amplifiers, and we don't fully understand all of them or where the thresholds are. The rate of change matters as much as the magnitude. Ecosystems can adapt to gradual changes over thousands of years through migration and evolution. But when change happens in decades or centuries, there's no time for gradual adaptation. Species either move fast enough or they go extinct. We're already seeing range shifts in thousands of species, plants flowering earlier, animals moving toward poles or up mountains, ocean species shifting to cooler waters. Some species are adapting successfully, others aren't. Current extinction rates are already elevated above background levels. Climate change adds another major stressor on top of habitat loss, pollution, and overexploitation. We're likely headed for another extinction wave. Maybe not as dramatic as the Quaternary megafauna extinctions, but significant. The paleoclimate record teaches us that rapid climate change is really hard on societies. Climate changes at the end of the Ice Age contributed to megafauna extinctions and forced major changes in human lifestyles. Droughts during the Holocene have contributed to the collapse of civilizations, and those were natural variations societies had no control over. We're causing changes faster and potentially larger than those natural variations. With over 8 billion people to feed and house, many living in areas vulnerable to climate change, the implications are staggering. Coastal cities face flooding. Agricultural regions face shifting rainfall patterns and extreme weather. Water resources are stressed by changing precipitation and glacier melt. Tropical regions could see temperatures exceeding human survivability thresholds during heat waves. The humanitarian implications are enormous, and the effects are unequally distributed. Those who contributed least to causing climate change are often most vulnerable to its impacts. But understanding the problem is the first step toward addressing it. We know more about climate now than ever before. We can observe changes in real time with satellites and monitoring networks. We can model future scenarios with increasing accuracy. And we have technologies available that could dramatically reduce emissions if deployed at scale. Solar and wind power are now cost competitive with fossil fuels in many places. Electric vehicles are becoming mainstream. Energy storage technology is improving. The challenge isn't really technological anymore, it's political, economic and social. Getting 8 billion people to coordinate on emission reductions, equitably distributing costs and benefits, navigating competing interests between nations and groups. What can the 100,000-year cycle teach us about our current moment? The lessons are both humbling and empowering. First, climate is sensitive to relatively small forcing changes. The orbital variations that trigger ice ages are tiny changes in seasonal sunlight distribution, yet they're enough to tip the system from one state to another when combined with feedbacks. We're applying forcing much larger and faster than orbital variations. The response will be substantial. It's just a question of how substantial and on what time scale. Second, feedbacks amplify initial changes. Small pushes can create large responses when internal amplifiers kick in. Albedo effects, carbon cycle responses, vegetation changes, ocean circulation shifts. These feedbacks work in both directions, amplifying both cooling and warming. We're triggering warming feedbacks right now. The more we understand about these systems, the more concerning the trajectories become. Third, there are tipping points in the climate system. It doesn't respond gradually and predictably. It has thresholds where behaviour changes abruptly. Ice sheets that seem stable can suddenly start collapsing. Ocean circulation that's been running for millennia can shut down within decades. Permafrost that's been frozen for thousands of years can abruptly thaw. We're approaching, or possibly crossing, multiple tipping points simultaneously. Fourth, climate has momentum. Changes we initiate now will continue for centuries or millennia, even if we stop emissions immediately. Ice sheets take thousands of years to fully respond to temperature changes. Ocean circulation has long-time constants. Even if we stabilised atmospheric greenhouse gases tomorrow, temperatures would remain elevated for centuries as the system slowly equilibrates. Sea levels would continue rising for centuries or millennia as ice sheets keep responding to warming already in the pipeline. This is uncomfortable to acknowledge. We've probably already committed to significant changes regardless of future actions. Some warming, some sea level rise, some ecosystem disruption is already locked in. The question is how much more we add. Every additional tenth of a degree matters. Every centimetre of sea level rise matters. Every species lost matters. The decisions we make now determine the magnitude of changes our children and grandchildren will face. Fifth, Rapid change is destabilizing for societies and ecosystems alike. Gradual shifts allow time for adaptation. Rapid shifts create crises. The late Ice Age megafauna couldn't adapt fast enough when their habitats transformed in millennia. Human civilizations have struggled or collapsed when faced with droughts or climate shifts lasting decades. We're creating changes far faster than historical natural variations. With interconnected global systems, infrastructure built for specific climate conditions, and billions of people dependent on predictable weather patterns, rapid change creates cascade failures across multiple systems. But the paleoclimate record also shows that life is resilient. Earth has been through dramatic climate changes before. Life survives. It adapts. It finds new equilibria. The planet will be fine in the long run. The question is whether human civilization as we know it will thrive or face massive disruptions that could have been avoided with foresight and action. And here's something crucial. We're not helpless. Unlike the megafauna that faced extinction, we have intelligence, technology, and the ability to understand what's happening and why. We can choose our response. The same human ingenuity that built cities and split atoms can be directed towards solving this challenge. We've overcome existential threats before. We survived Ice Age conditions through adaptation and innovation. We developed agriculture and transformed our relationship with the planet. We've created technologies that extend and improve human life. We're not lacking in capacity. We're facing a coordination problem. Climate change is the ultimate tragedy of the commons. Individual actors benefit from burning fossil fuels and emitting greenhouse gases, but everyone suffers the consequences. Solving it requires collective action at a scale humanity has never achieved. Getting nations to cooperate, aligning economic incentives with long-term well-being, overcoming short-term thinking and political gridlock. These are the real challenges. Some people feel despair. The problem seems too big, progress too slow, obstacles too numerous. That's understandable. But despair is paralysing and ultimately unproductive. A better response is informed determination. Understand the problem clearly, acknowledge its seriousness, then act. Individual actions matter. Reducing personal emissions, supporting clean energy, making sustainable choices. But individual action alone isn't sufficient. System-level changes require political action. Voting for leaders who take climate seriously, supporting policies that reduce emissions, holding corporations and governments accountable, adding your voice to the collective demand for action. Every person who engages increases the probability of meaningful response. The 100,000-year cycle reminds us that we're part of a planetary system much larger and older than human civilization. That system has its own rhythms and patterns that operated for millions of years before we existed and would continue after we're gone. But for this brief moment in geological time, we have the power to influence it. The cycle that shaped our evolution, that created the world our ancestors knew, is still operating in the background. The orbital mechanics haven't changed. Naturally, Earth would eventually return to glacial conditions, but we've introduced a new factor so powerful that we might have permanently altered the rhythm. That's simultaneously awesome and terrifying. Awesome in the original sense of inspiring awe, terrifying because of the responsibility it places on us. No species has ever had this influence. We're affecting the planet on a scale comparable to the astronomical forces that controlled climate for millions of years. What we do with that power in the coming decades will determine Earth's trajectory not just for our lifetimes, but for thousands or millions of years into the future. Future geologists studying sediment layers millions of years from now will see a clear marker of our presence. They'll see isotope ratios reflecting massive carbon combustion, extinction signatures in the fossil record, novel materials like plastics and concrete in sediment layers. They'll recognise that something unprecedented happened during this brief moment in Earth's history. Whether they'll also see evidence that we successfully navigated the crisis is still an open question. The answer depends on choices we make now and in the coming years. So where does this leave us? 11,700 years into an interglacial that should eventually end, armed with understanding of how climate works, actively changing it faster than natural processes typically do. The 100,000-year cycle that shaped human evolution being overridden by human activity. We've become a geological force. The story of the 100,000-year cycle is fundamentally a story about change, adaptation, and survival. For millions of years, Earth oscillated between frozen and temperate states on a precise rhythm determined by orbital mechanics. Life adapted to this rhythm. During cold phases, Megafauna evolved incredible specializations for Ice Age conditions, mammoths with their layered fur and molecular adaptations, woolly rhinoceros with their snow-ploughing horns, giant ground sloths engineering underground refuge systems, glyptodonts armoured against the most formidable predators. These weren't just animals surviving harsh conditions, they were magnificently adapted organisms thriving in the niches the cycle created. The mammoth steppe ecosystem supported biomass densities rivaling modern African savannas. Predators evolved hunting strategies to match their enormous prey. The system functioned, complex and balanced, for hundreds of thousands of years. Humans entered this world as just another species trying to survive Ice Age conditions. We weren't special initially, just another primate adapting to environmental challenges, but we had something that proved decisive: the ability to innovate culturally, to share information across generations, to solve problems through technology rather than waiting for biological evolution. Neanderthals showed us one path forward: physical adaptation to cold, robust bodies, large nasal passages, combined with cultural adaptations, fire, sophisticated tools, symbolic thought. They survived for hundreds of thousands of years through multiple glacial cycles. Modern humans took a different approach, less specialised physically, more flexible culturally, more innovative technologically, wider social networks enabling faster information exchange. Neither approach was inherently better. They were different strategies for the same challenge. Both worked for long periods, but when the last Ice Age ended and conditions changed rapidly, modern humans proved more adaptable. Or perhaps we were just luckier in ways we still don't fully understand. The megafauna extinctions remind us that even successful species with millions of years of evolutionary history can disappear when conditions change too rapidly. The creatures perfectly adapted to Ice Age environments couldn't adjust when those environments transformed in millennia. Some faced novel predators they had no experience with. Some lost habitat too quickly to migrate or evolve. Most faced multiple stresses simultaneously: climate change and human hunting and ecosystem transformation all compounding. The result was catastrophic. 70 to 80% of large mammal species gone within a few thousand years. An extinction event that reshaped ecosystems globally. But from those extinctions, something new emerged. Human civilization. Agriculture developed partly in response to megafauna disappearance and climate stabilization. Permanent settlements led to cities. Cities led to specialized knowledge accumulation, writing preserved and transmitted information. Technology built on previous innovations. Within a remarkably short time, we went from small hunter-gatherer bands to complex societies reshaping landscapes. The same flexibility and innovation that helped to survive the Ice Age also enabled us to dominate the Holocene. Now we face a new challenge. The climate system we thought was stable is changing in response to our own activities. We're conducting an uncontrolled experiment with our only planet. The 100,000-year cycle gave us a world to live in. It shaped the landscapes we inhabit. It influenced our evolution. It created resources we depend on, and now we're powerful enough to override it. That power comes with responsibility. The Ice Age taught our ancestors to adapt or die. That lesson remains relevant. We need to adapt our energy systems, our agricultural practices, our consumption patterns, our relationship with the planet. The choice is whether we adapt proactively through planning and cooperation, or reactively through crisis and suffering. Understanding the 100,000-year cycle shows us that Earth's climate is dynamic, sensitive, and full of feedbacks and tipping points. It's not a stable background that we can safely ignore. It's an active system that responds to inputs. For millions of years, those inputs were astronomical. Orbital variations pushing the system between states. Now we're adding powerful anthropogenic inputs. The system is responding exactly as the physics predicts it should. The question isn't whether climate will change in response to our emissions. It definitely will. The question is how much we allow it to change before we bring emissions under control. Every year of delay makes the eventual response harder. The ice age is over. The megafauna are gone. That world is lost and won't return. We live in a different world now. Warmer, more forested, dominated by one species that grew from ice age survivors into planetary engineers. The question facing us is what comes next. Do we use our power wisely? Do we recognise the lessons from past climate changes about tipping points, feedbacks and rapid transitions? Do we choose to act before crossing thresholds we can't reverse? Or do we continue on our current trajectory until the system forces us to change through crisis? The 100,000-year cycle still operates in the background. The orbital mechanics haven't stopped. Eventually, if we weren't interfering, Earth would slide back toward glacial conditions. But we are interfering. Massively. We've taken control of the wheel without fully understanding where we're steering. That's both our greatest challenge and our greatest opportunity. We have knowledge no organism has ever possessed. Understanding of how planetary systems work. Ability to measure and predict changes. Technology to modify our impact. The capability to choose our future rather than simply reacting to whatever nature throws at us. What we do with that capability defines us. It determines whether future generations will look back on this era as the moment humanity rose to meet its greatest challenge, or as a cautionary tale of a species that understood the problem but failed to act until too late. The cycle that froze Earth every 100,000 years shaped us, made us adaptable, made us innovative, made us survivors. Now it's time to use those traits. Not to survive the cycle, but to transcend it, to become stewards rather than just inhabitants, to ensure that the planet that gave us life remains habitable not just for us, but for the countless other species we share it with. The ice age is over. The question is, what kind of age comes next? And unlike our ancestors who simply had to survive the cycle they were born into, we have the power to shape it. That's the real lesson from studying 100,000 years of climate history.